Okay. In addition to working things out correctly, we also want to communicate them correctly. And we want to work on that just a little bit. Okay, like what does it take to communicate your solution here? Well, you could write it out. Express the vector 7, 12. And then a combination of the vectors in the set. You should officially write in vectors in the set, and I did. Okay, but this is enough. Okay, you don't have to get too worried with it. Well, you might say solve for C1 and C2. This equation. Then translate the equation. Everybody wrote down the right equation, real please. Okay, just talk a little bit about form. Okay, so you can write this equation as 3C1 plus 5C2 equals 7. And if you've established that you're halfway competent, which you've done, I know you can get from here to here. You don't necessarily have to write out all those steps, because the way you get from here to here should be pretty obvious, and I think it is to everything. But if you choose to write it out just to be sure, that's fine. Okay. If you can't directly translate it, then you know, I could translate it well. So correct me if I'm wrong. But anyhow, you have then 2C1 minus C2 equals 12. Now, there are lots of ways you could solve this. And when I stated the problem, I didn't say how. You could solve the simultaneous equations. You could add 5 times this to this, solve for C1, substitute in here, and get C2, right? That'd be a perfectly valid solution. You could write an augmented matrix and reduce it, which would be totally equivalent to solving your simultaneous equations. Okay? So they're just, a number of ways. You could even solve this for C2, plug it in here for C2, and solve for C1 that use substitution. We usually don't use it in this class because elimination is easier. You save substitution generally when you don't have linear equations, okay? Or a situation where you don't have linear equations. Okay, well, one way or another, you get your solution, okay? I believe everybody probably got a correct solution. Made an arithmetic error? Well, don't. Okay. But it's not the thing that I would penalize that, okay? Unless it misleads you. You make an arithmetic error that makes this thing look like these vectors are not a basis, then I have to penalize it a little bit if what I'm after is not what I'm after, okay? After the matrix equation. Even at that, you could write the correct matrix equation, you just won't be able to solve it. Okay, well, so an arithmetic mistake can lead you to change the context of the problem, depending on what that causes you to then do or not do. It could be a little bit of a penalty, just a simple arithmetic error. Of course, if you make an arithmetic error, it's not going to check out. It could cause you problems later. You want to get the arithmetic. Okay, well. Yeah. The matrix equation, this would just be 3, 5. -1. That's a little disturbing. I done something wrong here. What I do? Okay, hang on. Like I say, it's easy to make a mistake. These things should come out in columns. Stop record. It did, but it didn't say anything. Let me check my volume here. I thought I'd turn the volume off, and now I'm recording again, documenting my incompetence. Okay. Okay. Looking at this, I must have looked at it cross-eyed or something. Okay. Was not expecting that, and I kind of know better, I think. Okay, well, let's write it out, then you get. And we get this, so that 3C1 plus 5C2 equals 7. And 2C1 minus C2 equals 12. Okay, which translates into the matrix that I thought I was going to get. And I don't know what I did. I looked at something backwards. And I just pretended to do that so you'd know not to skip steps, right? Everybody believes me. Okay? I'm going to be. Okay, no, that was an honest mistake. Okay, so anyhow, this becomes the matrix equation 3, 5, 2, negative 1 times C1, C2 equals 7, 12. Okay? I guess I should have written it out. I gotta think about that one. How did I do that? So there it is. And you see that your vectors and your bases become your columns. And we've seen this previously. I always got it right before. Skip steps. Okay, V1 here. V2 here. Oh, sorry. V1 and V2 are numbers of the basis. V1 here. V2 here. So this is, as we saw earlier, the matrix V1, V2 times V1, C2 equals 7, 12. Now we'll write down the matrix for this, but it's just going to be these three vectors in your columns, or V1, V2, V3 in this case. You have a C1, C2, C3 because naturally you'd be adding multiple of this and multiple of this and multiple of this, and you do C1, C2, and C3. And I don't really need to explain that because everybody did it. Okay. There we have. Anyhow, just for reference, putting that in the video. Okay. So we say this is P. What is Px equals V. Okay. The form is Px equals V, or if we prefer, I'll explain why I'm writing it like this. Okay. Xb prime equals xb. Xb is the form of the vector relative, in this case, to the standard basis. Okay? So we could even, in this case, call this ds. Okay? For standard basis. Okay? And that's no ds. Okay, so this is 712. And it's a vector relative to the standard basis. Now I'll write out what that means in a little bit, but it just means if you take 7 times 1, 0, plus 12 times 0, 1, this is what you get. Okay? So your standard basis, of course, and you know this by now, is 1, 0, and 0, 1 for R2. Okay? This is what we're going to call the representation relative to this basis. And now I'll give this basis a name. This is your basis B prime. So this is the vector 7, 12 relative to the basis B prime. That's what sub B prime means. And it means is whatever you get here, you take the first coordinate and multiply it by this, and the second coordinate and multiply it by this, and you're still going to get 7, 12. Or you're still going to get whatever the vector was. But for one reason or another, and there's some incredibly good reasons that you'll see a little later in the course, you want to be able to express a vector in terms of non-standard basis, or to change from one basis to another. The ultimate reason for that, well, maybe not quite ultimate, but pretty much ultimate, is you want to be able to diagonalize a matrix. Okay. A matrix consists only of elements along the main diagonal, as simple as possible matrix. And we've got to talk about linear transformations, what all this means in terms of linear transformation. We'll be moving into that next week. Okay. Well, we'll be moving into preliminary. We're going to look at inner product spaces. Then we move into linear transformations. Okay. So my point is that this is a big deal. Okay. Let's say a little bit more about it. Take prime. That's big prime. That means all. Okay. So how do we solve that? We invert B. Keep in mind, for the reasons that I emphasized here about pretending to make mistakes and fix it, your P matrix is just going to consist of your basis vectors and columns, always, no matter what the dimension is. You want to remember why you're doing that so you don't get confused and put them in rows. Okay? Also, you want to understand what it is you're doing, be able to relate everything you're doing back to the basic set of to your basic equation for linear combination. Translate it into this form and then into a set of simultaneous equations, then into a matrix equation. Because that grounds you in the meaning of what all this is about. And it's a process of, you know, I've tried to emphasize, and I think successfully, because y'all are doing this successfully, okay? You get the credit. I just have to alone, okay? Actually, you're just little machines that I'm trying to program. It's all me. No, obviously not. Okay. Okay, so we get this. Well, this is easy to solve. Well, this is variable. How do you test whether P is invariable? You find its determinant. Is it singular? Is it non-singular? We get used to that terminology, that thing. We talked about it last time. Okay, so what is not a variable? Well, let's discuss this for a minute. I'm going to turn the camera off for a second.
Recording.
Okay, we had a couple of good suggestions and observations. You know, for example, it's not so, then you can't solve the equation. So then my question is, well, how do you express the thing in terms of the basis if you can't solve the equation? Well, the answer to that's a little logical twist. If the determinant of the matrix is not zero, this is not a basis. Okay? So the question is not intentionally misleading, because those kinds of questions always pop up. You got to be prepared for them. So just because you pose a question to yourself in the process of solving a problem doesn't mean there's an answer to that question. The question might be improperly posed, right? So when I said, well, how are you going to express it in terms of this basis if the determinant or if P is not invertible? That means the determinant's non-zero. And that means these aren't linearly independent. So this isn't a basis. And there was the answer. If you go on assuming that this is a basis, when the determinant of your P matrix is zero, you're going to spin your wheels for a long time. Okay? Okay, well. Okay, I kind of watched the word here. But you didn't have a basis to start with, so we're working with a false premise. The RE didn't come out very well. Okay. Understand? No. Okay. But now, assuming we did have a basis, and of course, you want to check that before you go trying to set this thing up, right? So one of the first things you're going to do is calculate the determinant of that thing to make sure you really have a basis. So that's an important suggestion. I might well put a question like that on this test, where I just say, well, This is B prime, so express this in terms of B prime, what B prime is in the basis. So your solution becomes pretty easy. You write down your matrix, you take its determinant and say, hey, that was the basis. I'm done. All right? And you are, that's full credit. You don't have to do as much work. It's convenient, but it requires a little bit of insight. So I'd be testing that little bit of insight if I put something like that on the test, right? Okay. Well, that's good. Y'all are doing great. Let's see what I can do to change that. Okay, well, we have this 3x3 matrix. So without writing it out in detail, you just take a lot of words to put down something that's equivalent to what I put down here. You use the same process, the same phrasing. But is going to be this matrix, okay? Now, in keeping with what I told you earlier, I really should show you what the three vectors are, right? So, better stick with what? So we want to document this much. I don't want to write this statement down without saying what B prime is. I'm just going to quote it from there, and then I realized we had some variables that were different. Okay. So I might even agree with one of your results, but probably not. Okay. So B prime is this. Now we can just say, well, we're going to put 8, 2, 4 in this column, -5, 13, 1 in this column, and 1, 0, 1 in this column. So what we do is find x B prime check to see if it is non-singular. Invert P so that x B prime equals P inverse x dx. Okay. Makes sense? Okay. Now, I see that our camera has again chosen to zoom itself out. That's kind of a good thing. If it hadn't, I wouldn't have been able to get those bolts on it. But let's zoom in to make sure we can read everything I just wrote. Okay, we good here. Okay. Okay, very good. Just to be sure, I might be repeating something that was on the video, but standard basis for P3 is this. Here's an alternative basis for P3. We want to express this polynomial in terms of the alternative basis. Okay? Now, this basis can be written as a linear combination of the vectors in this basis as an ordered four tuple. Okay? Because 1 times this and -1 times this and 0 times this and 0 times this give you this, right? Okay. So what are the other vectors? Can you write this one, and this one in terms of okay. Everybody got it. So, x plus x squared is this plus this, right? Which would be represented as 0 times this plus 1 times this plus 1 times this plus 0 times this, right? Then you'd have one of these and -1 of these, which would give you this. Then you'd have x cubed plus 1, which would be 1, 0, 0, 1. Okay. So, and let's be explicit about the connection here, because this is not just numbers, it's a little unfamiliar. But the point is that this is just going to translate into a matrix equation, which is numbers. I could have any x's in the matrix equation, because we already understand that any vector is represented in terms of this basis by a set of numbers, okay, that indicate how many times this, how many times this, how many times this, how many times this, and that gives you a polynomial, okay? So what would this polynomial be? Okay. Write that down, 2x cubed minus 3x squared plus 5x minus 4 equals what? Okay. So again, as I think I said to almost everybody, the question of how you express this as a four tuple, a ordered set of four numbers, is simply how many of these do you need, how many of these, how many of these, and how many of these to get this. And well, we start with this one, right? If we're going to do them in order so we don't get confused. It's be a disaster if we mixed up our order. Okay. So we have to have -4 of these, right? That's going to give us -4. Then we have to have 5x. Well, that'd be 5 of these, right? That's 5 of your second basis vector. So that would be 5. And then we have -3 of your third basis vector. So that means -3. And we have 2 of your fourth basis vector. Okay. Now, we want to express this as a linear combination of these. A reason that I'll leave you to think a little bit more about. Here are 4 basis vectors. I mean, here are the 4 vectors. Okay, here are the 4 basis vectors in terms of this basis. If you do by analogy with what we did with the 2x2 and 3x3 matrices, you're going to see that these vectors are your V1, V2, V3, and V4. As a matter of fact, I don't think I'm going to write down the matrix. matrix is going to have these things in a column, but let's make sure in this context that we understand why. So when I say express this in terms of this matrix, in terms of, in this context, means as a linear combination of, okay, these vectors. So we know how to write a linear combination. We want to have this is your linear combination, your arbitrary linear combination here, and this is the target expression that you want. So this can be written then as what? C1 minus C1x plus C2x plus C2x squared plus C3x cubed minus C3x squared plus C4 plus C4x cubed equals 2x squared minus 3x, 2x cubed, that's cubed. 2x cubed minus 3x squared plus 5x minus 4. Just writing what a linear combination means and understanding that we want a linear combination of these that equals this. How's that going to give us 4 equations? Well, we've got C1 here. That's C1 times 1. Yeah, I don't think I want to write about that detail. Okay, what same constants do I have? I have C1 and C4, right? So we have C1 plus C4. And then what x terms do I have? Well, I have a negative C1x and a C2x, right? Do I have any other x's unadorned with exponents? No. That's all I have for just multiples of x. And then I have C3, negative C3, but I have C2 x squared and minus C3 x squared. And then on x cubed, I have a C3 plus C4x cubed equals 2x cubed minus 3x squared plus 5x minus 4. And this tells me this has to be true for all values of x. This tells me C1 plus C4 has to equal negative 4. Right? And negative C1 plus C2, that's times x. I didn't write the x. But that's got to be 5. And then C2 minus C3 has to equal negative 3. And C3 plus C4 has to equal well, this translates It's a matrix equation. Left-hand side is going to be matrix times your C1, C2, C3, C4 vector. And that's got to equal the target vector, right? That's barely right. Hopefully you can read it, you understand what's there. Well, what's my matrix have to be? Well, I need C1 plus C4 in the first row, so that the first row will be equal to -4. So that means I need a C1 and a C4. So I multiply this by this, I get C1 plus C4, and that's got to equal -4. I think you understand matrix multiplication well enough. If that's clear. Let's make sure. Then we have a -1, 1, 0, 0. To give us just a negative C1 plus C2, which has to equal 5. And then we have C2 minus C3, which is going to give us this vector, right? This row vector. And then C3 plus C4. Okay. Now let's look at our columns. Column is 1, -1, 0, 0. Right there it is, right? That's this vector. So this vector is in a column. Second column should be this vector, 0, 1, 1, 0. Well, 0, 1, 1, 0. Third column should be 0, 0, -1, 1, 0, 0, -1, 1. Fourth column should be 1, 0, 0, 1. Okay. So this is it could also be written as the column vectors V1 through V4 multiplied by your vector in terms of the basis B prime. Equals X ds in other words, in terms of the standard basis. Okay. Their book doesn't use any ds. Okay, I do. In other words, they're just going to call this basis B. We're going to call this basis B prime. And this basis doesn't even have to be the standard basis. I'm using the standard basis here because it simplifies this construction. Okay. And you might or might not have time to talk about what to do, but isn't the standard basis? That's fairly easy to understand. Okay. Okay, so and of course, this is, well, we're going to go up here so we don't have room down here. Dx B prime equals X. Yeah, okay. Little jumbled, but that's not uncommon. Now we do want to find the determinant of this matrix to make sure we really have a basis. But that's a pretty easy determinant. You can just expand it on the first row. You have a 1 here, and then this matrix is a subdiagonal matrix, so the determinant is just the product of the diagonals. Okay, so we have a 1 times -1 gives us -1, right? And then we have a -1 because it goes positive, negative, the i's and j's, evens and odds. And then it's times this minor. Okay. We're looking at it right. It looks like it comes out 0, but I know it does. Okay. So anyhow, you work it out. We'll disturb it. Looking at something wrong. Okay. So anyhow, make sure that's invertible. And invert it. Okay. I don't think any of these can be expressed as linear combinations of the others, but maybe. If that is 0, then some of these are linear combinations of the others. Okay. However, whatever. When you solve this, you get the C1, C2, C3, C4, which are the multiples of these vectors, these polynomials that you need to express this. Okay, it's maybe a little unsafe for me to have just used coefficients of 1 and -1 there. I'd have thrown a 2 in here and there. Then I wouldn't have the danger because, looking at that, it looks like that determinant is 0. So I wasn't careful enough when I set up this basis. But you get the idea. I wanted to keep it simple so the matrix be simple. So you understand how to do this in terms of a non-standard basis, a basis that isn't a basis for R3, R4 in this case. Okay. Now, among other things, this is starting to tell you, we haven't proved it yet, but P3 is in this sense totally identical to R4. As we mentioned before, these are linearly independent. You can't get any of these as linear combinations of the others, and they span P3. So we do have a basis. That basis can be identified with the standard basis of R4 in such a way that everything gets written out outside. And now you're just working in R4, but then you translate back to what this means in terms of P3. Right here, we're working in R4. Now, you say these vector spaces are isomorphic, but before they have the same form. Iso means same, morphic means form. But we haven't defined what that means, and we haven't yet talked about linear transformations. Okay? And linear transformations of vector spaces. So we can't really get to that, but again, keep that in mind. Because we can represent vectors in P3 by numbers and vectors in R4. These things have, the two vector spaces have exactly the same form, so we can do anything we want in R4 and translate it back into P3. Any question we want to answer about P3, we can answer in R4. And that's handy because it allows you to kind of geometrically visualize what's going on. Now you can't visualize R4, but you visualize R2 and R3. And that's where most of our intuition comes from, R2 and R3. And we'll be doing that as time goes on. Your book also gives the example, and this isn't the example from the book. This isn't the basis. If it is a basis, which probably isn't. Okay. But you'll see the example. That's the first example on the last page, basically, the last screen of the text for section 4.7. Your book also tells you that you don't necessarily have to invert the matrix. You can set up an augmented matrix with the P matrix and the identity matrix and reduce it, and that gives you your inverse. And if you have a non-standard basis over here and a non-standard basis over here, then you can put one basis here and the other basis here and reduce bounded identity, and you get the matrix that connects those two bases. Your book and I both prefer you understand it in terms of this notation, because this notation is going to get real important later when we talk about things called similarity transformations, which lead to diagonalizations in good cases. That lead to great simplification of your calculations. Okay, well, that's probably all I need to say. I was going to say your book does an example of M4 or M22, a four-dimensional space of 2 by 2 matrices. You know what the standard basis is, and it all translates much more intuitively because it's just numbers than this example. But function spaces are amazingly important, especially infinite dimensional function spaces. I'll maybe give you a little flavor of that later on in the course. Okay, but we'll see a little bit of that when we get into inner product spaces. So I'll save it for then.